and I'll introduce Robert very quickly for those who do not know him. He's a distinguished professor of psychology at Indiana University. He won several awards from the APA and the National Academy of Science. His interests include many things, like decision-making, computational modeling of human cognition, and concept learning and representation. And I believe that today's talk more or less revolves around this latter aspect of them. So I'll leave it to you, Rob. So the floor is yours.
Okay, great. So it's wonderful to be here. Thanks for showing up and bearing with the technical water difficulties. And it's been beautiful to be here at Bristol. I'm here for the day and would love to be talking with other folks. So just swing by psychology. I'm not going to monitor chat, so let me know if there's anything I should be responding to. I guess an issue, so I guess the person that I should emphasize here is Eric Weitenauer. The work I'm going to be talking about was his dissertation. This has been a long time coming. So he started his dissertation at Bielefeld back in 2013, and the article just came out last year. So yeah, it's been 10 years in the making. And since then, Eric has moved to Indiana University, where he's a CEO of a company called Graspable Mathematics that is actually, in some ways that maybe we can talk about, is building upon the dissertation ideas that I'm going to be talking about here and developing them for an algebra tutoring system called Graspable Math. Over in Bielefeld, Eric's primary advisor was Helga Ritter. And something that's been of interest to us for a long time is how to think about concept learning in a flexible domain where people have to change the descriptions of the concepts while they are learning them. So there's a story which would be very convenient if it were true, but I don't think it's true. And that story is when you want to compare objects because you want to put them in the same category, you want to figure out how similar they are to each other, what you want to do is like give all the descriptions of one of the things and give the descriptions of the other things, and then just compare those descriptions and find out where there's overlap and where there's differences, and that'll tell you whether they belong in the same category. And unfortunately, things are not that easy because we believe that when you're forming concepts, it actually changes the descriptions of the objects that are entering into that category or for the similarity. So most models, all the models that I know of, like concept learning, which is one of my areas of research, treat perception as separate from and typically completed before the processes that create and use the concepts. And I don't want to just point at others as making this assumption, like my colleagues Nosovsky and John Krushke, Jerome Bussmeyer, but it's also true in almost all of my work too, because it's just such a convenient assumption to start with the descriptions of the objects. But I would like to argue instead that there's this important idea that a big part of humans' creativity and intelligence has to do with coming up with these useful descriptions in the first place. And there is a tradition of this in two areas in machine learning and AI, and neither of them is exactly what I'm talking about. First, there's an interesting tradition, which I was super excited when I first came across it as a graduate student of constructive induction and artificial intelligence. I associate Larry Rendell, Rizard Mikalski with this movement. And what they argue is we need systems in AI, this traditional symbolic AI of the 90s, that creates new descriptions. And their systems do create new descriptions, but only in a very trivial sense that if you started with a descriptor of like white and another descriptor of square, it could create new descriptions like white and square or white or square. And so that's really what they mean by constructive induction, that you're just using Boolean concatenators to create new propositions. And so yeah, but this is rather limited. And there is also, on the other hand, modern deep learning systems that create internal representations in order to support their categories. But in contrast to what I'm going to be talking about, they oftentimes require a huge amount of training. And the kinds of descriptions that they're going to be creating aren't going to be useful for our purposes of trying to explain how you're going to learn the categorization of just these, I don't know, 20 objects, say. And there's just this example down here below is from ancient work from us, just showing how the comparison process does create new descriptions of objects. So for example, when you compare those two objects on the left and middle, people oftentimes say, what do they have in common? They all have, both have 3 prongs, okay? Whereas if you have people compare those objects, they'll say they have in commonality that they both have 4 prongs. They give mutually exclusive descriptions to that middle object, depending upon what it's compared to. And so that's some reason to say that the process of comparison actually does create or help build up the descriptions of these objects. Okay, so our test domain for looking at issues about building up these descriptions while you're learning a concept are I don't think maybe famous is the right word, in cult status, maybe. Famous among nerds. What are these Vanguard problems named after the Russian early AI researcher from the 1970s, Mikhail Vanguard. And the problem for that Vanguard proposed was you got a certain number of scenes that belong on the left side, a certain number of scenes that belong on the right side, and you have to find the rule that will correctly sort them, tell you whether you belong on the left side or the right side. So in this case, there's 6 entities, scenes that belong on the left side, and there's 6 entities that belong on the right side. Can somebody come up with a rule? And this could be from the Zoomers too. Maybe Fabio will tell me if somebody comes up with a rule.
Everything has to be big.
Yeah, so on the right side, everything is big, whereas the left side contains some small objects, right? So that's the game. They can get, this is a slightly harder problem.
Well, black circles on the right, black triangles on the left.
Yeah, very nice. And so this is black object is triangle, black object is circle for the left and right respectively. Not so bad. That's very, very fast, Steve. I'm impressed. Okay, here's a harder one. And this just is, I'm trying to get at, so our system can easily handle these problems. So would Mikulski's system could have handled these because it's likely that you would code things for their size and it can build up these Boolean expressions of circle and black. Say, okay, Mikulski's system could not do this kind of problem, and maybe you can't either. This is medium difficult. They get arbitrarily difficult.
They get symmetry or something.
They get super difficult, and anything goes. So you have no idea what is the proper description. And as you try to solve this, you're probably having to come up with new descriptions that you hadn't originally thought of when you first saw the problem. And so that's what makes it an interesting domain for us.
Well, the ones on the left are letters, sort of. The ones on the right are.
Is that a letter? Okay.
Sort of that.
The ones on the right have a right angle as the final angle.
Yeah, very good. Yeah, so that's absolutely right. So the ones on the right, they will end, the beginning line segment and the end line segment are at 90 degrees from each other.
Okay.
And so that's true for like that is 90 degrees from that. Whereas they're, I don't know, 100, they're parallel for the ones on the left side. Very good. And so then the question is, how do you come up with that kind of description? You didn't originally think about coding that, but that along with millions of other properties could come out. Here's one that I liked from my colleague at IU. Doug Hofstadter, and to my mind, Doug Hofstadter was super important in popularizing Bongard problems. They were a big part of his '79 book, Gödel, Escher, Bach.
That pencil isn't part of the problem. That's just your cursor.
Yes, I think so. Oh, yeah.
Yeah.
Oh, there's two sets of, yeah, there. The ones that are on the same side as the pencil. And the reason why I'm interested in this one is because you are very arguably creating new entities or new descriptions, I would say new entities, in order to solve this one, if you solve it.
Is this actually Bongard problem generated? Or
No,
just-
so yeah, good question. So this is a problem it's called Bongard problem, but it's not one of the 100 problems that Mikhail Bongard created. So he had his own set of 100 problems of roughly ramping up difficulty. And this is not one of them, but you know, in the same way that you can have Jell-O desserts that aren't made by Jell-O. So this is a Bongard problem not made by Bongard. This is created by Doug Hofstadter, and I should say for the nerds in the crowd, there is many, but this is one of the archival locations for people to submit their own Bongard problems and see Bongard problems that have been created by others, and there's hundreds and hundreds there. So people like proposing them and then solving them. And it's fun to do several of them. It's good to do them in random order so you don't get certain priming effects. If you do this, have I stalled long enough so that somebody has a solution?
It's tough.
It's a tough one. So what would make it easier is if I added lines that you could have added yourself. So I'm adding these lines that may make you notice something.
Well, yeah, they're not.
Are they rotated versions of the apex? The apex?
No.
But the angles
Because
are all.
those two look like they are all identical. Or
Something is identical. Yeah, there's some notion of identicality that's at play here.
Still don't get it.
Maybe it's use your words. More.
it's a rotated version pinned from the apex of the.
Yeah, okay, maybe. Yes, okay, I do see what you're getting at. The simpler way of expressing your notion, though, is isosceles. So the ones on the left are isosceles triangles and the ones on the right are. So yes, they are, but it doesn't, but I'm not telling you which is what Josie was telling is the apex. So in this triangle, for example, it's this line that's the same length as this line. For this one, this line is the same length as this one.
Oh.
This is equilateral. For this one, these two are the same length. So it doesn't always have to be, yeah, so, right, so very difficult problems. And so you don't, and the nice point is you don't have to get very complicated for there to be, you know, sort of an unspecified open set of descriptions that would be readable off of this. And what I would like to say is that this isn't just a game that nerds play, although they do. This is also really super important to mathematics and science, and also new creations in art and music too. In science, there was from John Snow this incredibly important observation that all of the people who were contracting cholera back in the earlier epidemics that we had, preceding the modern epidemics that we're living under by more than 100 years. And John Snow came up with this new description that wasn't there in the cases, but he came up with this idea that they're all within a short distance of a particular well in London that was tainted with cholera bacteria. Maybe even more impressive to me is, I guess, are kind of around the same time, Maxwell was coming up with his kinetic molecular theory of ideal gases. And here he's hypothesizing, he's creating this new description that you're looking at this invisible gas, but really what's underlying there are these billiard balls, these individual gas molecules that are bumping into each other. Sometimes they're bumping into the wall, and when they bump into the wall, that's what we know of as pressure, right? So that is a real world case where you're creating new descriptions that are by no means trivial. Okay, so this is our variant. These aren't just Bongard problems, but they're a particular kind of Bongard problems in which the normal laws of physics apply to them, including things like collisions, momentum, gravity, impulse. So all of those physical notions apply, in this case, in 2 dimensions. And so maybe people have solved this one, and I'll just tell you. So here, if the normal laws of physics apply, for the objects on the left, the objects would end up touching each other, and on the right side, they don't. Even after the laws of physics apply, they don't end up touching. And this is fitting in with a huge trend in modern cognitive science to study situations in which people have to engage in this kind of internal physics simulations. So there's pretty good evidence that we do some version of this. From the class view, we don't necessarily think they're always veridical simulations that we're running in our mind, but there's something like this simulation process. And for our purposes, these physical Bongard problems are interesting because it makes our point even the more strongly that in order to come up with the correct rule, you really have to engage in an internal process to come up with new descriptions that weren't there. Like, you don't know ahead of time until you run the simulation that these objects will end up together. Okay, so this is what we're interested in doing, and there's at the core of our approach to Bongard problems is the idea that you're getting context-dependent descriptions in our model, which is called PATHS, which stands for something. The 3 kinds of context that are important for us are there's context shift in your threshold for what you're going to call an object or a relationship between 2 objects. And here we use a certain fuzzy logic that's been created by this AI researcher, Irene Block. Basically, you can feed in any kind of shape that you want, and it will tell you in intermediate degrees how left of every pixel on the screen is relative to the object pixels that make up this red horizontal line segment, for example. And in her logic, this would be the region that would be right of, which is also fuzzy, it's graded. When we're actually trying to come up with a spatial relation of right of, it turns out that it's useful for us to create the sort of the difference. You can barely read that, but that says the right area minus the left area. It's just a better cue than just using the right of area by itself. Maybe this U shape gives you a good example of why. So if you just apply Bloch's calculus, all of the areas that are white would be good right-ofs. And this area is good right-of because there's a lot of pixels that this is due right-of. So if you want to actually get a more discriminating use of the spatial predicate right, it would be better to subtract out the left region from the right region, and that will cause this more psychologically plausible right-of region. So that's one kind of context dependency that we get is does this count, let's say, does this area here count as right-of? Well, we can change that threshold. It depends on how much evidence we have. So that either might be right-of or might not be in certain contexts. The big one is that descriptions that are frequently used for scenes in a category will tend to be tested on other scenes from the category. So if the guy on Zoom who came up with the 90-degree solution, he may have seen it in the context of one relatively clear-cut squiggle, but then he would apply it to other squiggles to see if it was right. And that's a critical kind of category sensitivity. And the final kind of context dependency that we'll get to is that you're going to be particularly influenced by like the temporal or the spatial context in your interpretation of one scene. So you're going to tend to pay attention to similarities between two scenes if they belong in the same category on the same side in a Bongard problem, and you're going to tend to dissimilarities if two either temporally or spatially adjacent scenes belong in different categories. Yeah.
I find that graph there hard to read from a distance. It's very small.
Yeah.
So okay, so the red stuff, that's the object.
Yeah, so the red is the landmark object, and you're trying to
that has
out,
a little thing above it or in it or something.
Ignore this thing over here.
Oh, so what are the red dots on the right? The red dots in the center and right.
Like you mean that the U shape here?
No, there's a red dot in the middle of the U.
Oh, I think I just added that in there.
Just an accident.
Oh,
I just put that in there right now.
Okay.
So I was putting that in there to show like that this problem, most humans would not consider that a good example of right-of. And
right of what though?
of the U shape. So there's a red U here.
Yes.
And so now what are all of the, let's say there was a X over here.
Right.
Would you consider that right of the
Yes.
U? The answer is yes. And the answer, and this is given by, that would actually be given by blocks.
Okay, so there is another, so the red dots aren't entirely coincidental. In other words,
They were part of my explanation, yeah. That was.
But what does the participant see? That's what I'm.
So a participant would see some object that was anywhere in this entire two-dimensional surface.
Oh, okay.
And we're trying to figure out whether the participant would call it.
And the U is always invariant.
In this case, so we're just imagining, so we're trying to figure out, do we apply the predicate right-of to different positions in the space?
Okay.
Yeah.
So there will be some dot or something floating around.
Right, there will be some,
Okay.
So there's some sort of target object that's going to be judged relative to the landmark object. And so this is just how you would calculate a spatial relation. Yeah.
So the question to the participant would be, is this right of yes or no, or where is this on space? Like, are they free to?
So in our context, so people have done work on that. People have done like forced choice spatial judgments, like Gordon Logan has done experiments like this. For our purposes, the task is just solve the Bongard problem.
Okay.
And the solution to the Bongard problem could be something like the triangles are always to the right of the squares. That would be the task. Okay, so here's an example of maybe a Bungard problem that exactly does that question. And so the point I'm trying to make here is, well, so here I'll spoil this for you. The answer to this Bungard problem is that on the left, the triangle is above the rectangle. So like the triangle, according to this fuzzy logic, the triangle is above the rectangle, good enough for our purposes. Whereas on the right side, the triangles are always to the right of or beside the rectangles. But the point about our context-dependent descriptions is we could actually move one of the scenes from the left side to the right side, and where we formally describe this triangle as being above the rectangle, now we would be describing it as being right of the rectangle. And people will readily give both of those solutions. They don't give a different interpretation to the same scene. So people wouldn't like it if that same scene was in the same Bongard problem, but across two Bongard problems, they're happy to give it different descriptions. Okay. So here's a high-level description of what goes on in this algorithm. And this is, if you're familiar with regular computational cognitive modeling, this is going to feel very highly parameterized because it is. But that's because we're trying to do something difficult. Because there's lots of descriptions that are possible. So we are not going to be engaging in the game of fitting parameters of the model to maximize their fit to humans, because there'd just be too many parameters. So so that as a preamble, this is going to be a very complicated model by some standard conventions. But at a high level, the kinds of activities that happen is that the model could decide to try to perceive a new feature. It could look at an object within a scene, and it could try to apply one of its pre-existing predicates to that object. And then it would just sort of randomly select a target and a feature, and then apply that feature, yes or no, to that target. And it could also perceive features using this physics engine that we already argued was important for people. And it will create new hypotheses. Hypotheses like maybe anything that's square belongs on the left side. There's another stochastically chosen action that it could choose, which is to actually check hypotheses, which is it's got this list of hypotheses that it's entertaining, and it can decide to check that hypothesis on the current scenes that it's looking at, or it could decide to advance the scene pair and check that hypothesis on another scene pair. And the final thing it can do is it can recombine hypotheses. So it can either adjust a relation. Maybe I was too strenuous in arguing that close had to be this close. Maybe this close was enough. It can adjust thresholds like this, and it can combine features in a sort of a recursive first-order predicate logic representation. So if it had originally an idea that maybe it's important that an object was stable, maybe that was too general. Maybe it's the square has to be stable. So it can then take a general hypothesis and it can refine it by adding conditions. So
this seems like it's a sequential, I mean, in my intuitions, I do this sequentially. I have a hypothesis, okay, I try it, and then, oh, it doesn't. But it sounds like the way you're describing it, you're just stochastically picking one of these processes.
Right. So any sequentiality is going to be an emergent phenomenon from this. So any one of these steps is sequential, I guess you could say, but you're totally right. It could be hopping back and forth between doing the left thing and doing the middle thing and doing the right thing. But there still is a fair amount of sequentiality that emerges out of that, that if there's a very promising hypothesis because it's found in, I don't know, 5 out of the 6 scenes in one side of a boundary problem, then it will be very tempted to try it out on the remaining scene.
Does it come with a built-in set of hypotheses, or is it a?
No, so it's, what is built in are these things. So it has a built-in set of things that it can notice, like spatial relations, like left and right of movement directions, movement speeds, collisions. An important thing is groups, so it can group different objects within a scene because they all have the same feature or they're all in a particular location, relative or absolute. So these are the things that are built in. I'd love to know how to create new ones of these, but the system doesn't do that. So these are now built in.
So do you have an example of a hypothesis?
Yeah.
There's a lot of elements here, so how?
Yeah, so I'm going to, let us switch over to the demo part of this. So the cool thing about this is available for anybody who wants to play with. So this is runnable. You can run it on our problems. So we put in the problems that we described in the paper, but you can also import your own problems. It takes SVG representations, which is loaded theoretically, because SVG representations, what is that? Scalable vector graphics. So it comes with the object segmentation problem already solved. So it comes with objects that have uniform colors for us, and it's got their XY locations. So it's not a bitmap, or it's not a pixel-based representation. But we're arguing that there's still a lot that has to be read for it, starting with this SVG representation. So so this is the boundary problem on the left, and these are the features that it has that are. There's if this isn't the full version of it, would be more features, but these give you an example of some of the features that are there, and you'll see the hypotheses coming on the screen. So when we run it, then so do people solve this problem? This isn't such a hard problem. Anybody on Zoom?
Left side is 1 object, right side is 2 objects.
Very good.
Okay.
That's it exactly. 1 versus 2. That's pretty. Okay, and maybe Pat's isn't quite as fast as you were, but Pat's gets the right answer, and the way to interpret this is only in the left scenes. Yeah, okay, so this is a good example of it being more complicated than it need to be. So the way it expressed it, there are objects that can move up that are, and the number of them is 1. And that's true for the scenes on the left side. And it didn't need to mention that thing about being able to move up, but it did in this case. If we ran it again, it ended up with a simpler description. This time it focused on the right scenes. There exists objects that are 2 in number. So it is stochastic, and we don't know what it's going to come up with. So these, to answer Stephen's question though, these are the hypotheses that it was considering on the way to correct the right answer. E is an existential quantifier. A is the universal quantifier. And there's also a uniqueness quantifier that's not typical in first order predicate logic, but that means there's exactly 1. Which seems important for people in certain cases. And so you can also see how you get sort of these recursively embedded hypotheses here. So the way to read this is objects that are left of any object at the end. So it came up with this very open-ended descriptor, any object, and then it inserted this in this description, and it turned out not to be very useful. So what you would really like is descriptions that don't just apply to the left and the right scenes, but only apply to the right scenes and not the left scenes. And ideally, in this case, there should be exactly 16 pass tests. In this case, there were. So that's an easy problem. I'll show you maybe. Here's a slightly harder problem. We can do a John Henry race. John Henry is not a British idea.
The objects on the right will come to a halt, right?
Oh,
Stabilize.
exactly. Oh, yeah. So yeah, you beat Pats because I didn't even start Pats. So you won the John Henry race. So John Henry was this lumberjack who was fighting against the steam engine and to see who could chop more logs. And I think he won, but then he died. So I think it was a Pyrrhic victory. Not to jinx you, but that is the fate of all humans eventually. But yeah, you slaughtered Past in this case. And so only in the right scenes do there exist objects that are on top of any object at the end. Yeah. So I think that's saying a little bit more verbosely than what you said. So on the right side, there is an object that is on top of another object at the end, once you run this physics. And so it actually contemplated quite a number of hypotheses in order to get there.
Does it have some physics engine? Like how does it?
It sure does. Okay. Yeah, it's got Fox 2D is the specific name of it.
Oh, it does have physics.
It sure does. Yeah,
Okay.
yeah, critically important. In fact, and there's no way it could. So you can run the physics engine on it. So you can see what, and you may have seen it actually sort of imagining the physics while it was doing it.
Bounce.
Right, so you can change some of the parameters of the objects, what they're made out of. Yeah, and so that it's critically important that it has that, and it would not have been able to do it otherwise. You can also notice that and this goes along with some of the empirical results, it's comparing the scenes in pairs. So in this version, it's always comparing across scenes, but we have another algorithm which is deciding what pairs of scenes it's going to be looking at any given time. And that's in order to account for some of the human data where we force people to see them in pairs as well. And maybe I can get to more of that.
Sorry,
yeah.
Does it have an assumption that they are independent objects or attached? Because my problem with looking at it is that I first need to puzzle out whether they're actually attached or not.
You mean at the beginning?
Yeah, when it starts.
Oh, like here, like this could be attached to that.
Yeah.
Yeah, so that is a good example of we're feeding in some extra information by virtue of making these SVG files. Because in the SVG representation, you're specifying that it's two separate objects, meaning it won't be inclined to interpret this as one turtle-like object that has two colors on it. Yeah.
So it has got that written in, whereas we have to puzzle that out.
That's right. So, yeah, and my only justification for this is that we kind of feel like there's quite a lot of work in computer vision that has done a pretty good job of giving you the objects. That, there's a lot of systems out there that do figure ground segmentation pretty well. Now, would there also be these kind of context dependencies for figure ground segmentation? Probably, and we are not able to account for those. If we were to plug in somebody's figure ground segmenter, then we would be just treating it as a plugin rather than something that could be top-down controllable. Yeah, but yeah, so our only justification is somebody else would have solved that problem for us already. Okay, so so this gives you a pretty good idea. So I guess I have to do some of the regular cog sci kind of thing to do. So we compare it to people, and there's a lot that could be said about this. The correlation is pretty good if we ignore problem 31. So 31 can be gotten from the paths model, but it feels to us like humans might have some built-in primitives that are different from the ones that we're building in. These are the so I showed you anyway the primitives that it has built in. So that. And so this is the exact problem that is way easier for humans than it is for paths. And if we leave this one out, then the correlation is pretty high for both response time and accuracy. So for people, on the left side, the circle is free to escape. And on the right side, the circle is not free to escape. And paths can get there, but it has to get there by sort of imagining a fragile string, which is connected to the circle. And it imagines that there's a way of pulling up this string on the left side that keeps the string attached, whereas on the right side, there's no way of doing that. So that's the convoluted kind of logic that paths has to get to in order to get to the answer, which is why I don't know why people can do it better. People just have this idea of it's covered.
It's like agency.
Agency?
Yeah, and intentionality. It's very similar to some of the infant problems around intentionality, about what infants predict or perpetuate.
But how do you see intentionality here? That's interesting.
Well, you could just imagine the ball wanting to get it.
That's the one. Okay. So like who is that early
There's
Heidel?
quite a big literature on
Zimmel and Heidel?
yeah, that's the work.
Yeah.
There's also Gershli and Sachibra's work
Right,
on
okay.
infant intentionality. Yeah, you know, these little simulated scenes.
Okay, that'd be interesting, possibly.
Big ball wants to get to small ball wants to get to big ball. Does it have the rational intent? What happens when you remove an occluding barrier?
Okay,
Do they
yeah,
have an infant surprise that you will have an irrational jump? Yes.
Okay, I like that. So yeah, it fits into this idea of a very human notion of being free versus constrained. Yeah.
Also that you've got rational acts.
And how much of these infants that discover?
Well, they were trying to argue for it to be agency. It's a bit more teleological, but they're 6 to 9 month olds.
Really?
So,
They have
yeah,
that?
they've got these sorts of, if you believe the violation of expectation literature. Not everyone does.
So, okay, so the model is doing pretty good. The final thing I want to say about the kind of the detailed tests of the model that we do is we, for both the humans and the model, as you saw, we're presenting them in pairs. And for humans, we can arrange the problems in different ways. You may have noticed for the Bondar problems that were in the software, again, they look mostly like this upper left-hand corner kind of problem, where all of the scenes that are in one row look alike. They have some kind of similarities, and so all the row 1 things all have a single object that's a square or a rotated square. And like on the row 3, there are all of these kind of tower-like things. And so we're interested in just issues about like the positioning of those. And well, I guess I've already given you the answer to the question of which is easier and easiest for both the model and people. The easiest kind of arrangement is to have dissimilar scenes that belong on the same side, that are close to each other or likely to be compared to each other. And it's good to have similar scenes that belong in different categories that are likely to be compared to each other, either because they're close to each other in time or in space. So this comparison helps people because they look at this and they say, well, it can't have anything to do with square because there's squares on both sides. It can't have anything to do with hills because there's hills on both sides. So maybe it has to do with where the square is relative to the hill. So maybe that can help build the explanation. And so actually having dissimilarity between these scenes that belong in the same category helps too, because it means that you're less likely to come up with overly restrictive hypotheses that work for a particular two pair of similar scenes, but doesn't generalize. So so what this is saying is that for both humans on the left side and paths on the right side, between categories similarity is helpful. The y-axis is difficulty, so a low value is good. So you're doing better when the between categories similarity is high rather than low, but you're also doing good when the within categories similarity is dissimilar rather than similar. And that makes a certain amount of sense. And I think both the humans and the model get it for the right way. So just in terms of being able to winnow out hypotheses, between category similarity is helpful.
It's kind of weird though, isn't it? I mean, mine took, if you had asked me this beforehand, right?
Yeah.
I would have thought, well, I can pick up differences between categories more easily if there's a big difference between them.
Oh,
So in other words.
but it could not be, it might pick up the wrong one. But because let's say, like you might look at this one and this one, it's easy to find a difference. One has circles, one has squares, but it's not going to generalize to the other ones.
Okay, so that's what it is.
Yeah.
Right. Good.
We have 7 minutes left.
Yeah.
Well, we have the room is booked for 2 hours, but I guess some people will do that too.
So I'm pretty much done. So there's my conclusions. So so the core commitments that I think are what I'd like people to take away from this is that descriptions should be continually created while the concept rules are being constructed. Unlike, I would say 99% of work in my field of concept learning, we talk about 3 different ways in which context is influencing the descriptions that people create. So the new descriptions, they're really coming out of these perceptual routines and these simulations, and it's not just sort of trivial recombination or this Boolean concatenation of symbolic AI. And so I'm very interested in this idea of Simone Ullman had this idea of visual routines for detecting things like spatial relations and support and stability. So that's where we're coming from too, I believe. So at the same time, it's important to have explicit rules for our problems at least, and to talk about a grammar for creating those rules in. And maybe it's an interesting approach to think about concept formation as an open-ended search for these compositions of these descriptions that are built up. And final, we do have this testable code. You can swap in your own SVGs. It's a fun task to give students to see if they can stump paths. And unfortunately, it's pretty easy to do that. But we're working on version 2. Okay, thanks.
We have a question from
Konstantinos, yeah.
Yeah, do you want to ask it with your tongue and lips?
Yes. Can you hear me?
Yeah.
Yeah.
Yeah, thank you very much. So very interesting topic. While you were discussing the differences between the humans and paths, I was thinking of the 246 ways on task of induction, right? One of the classic ones.
Yes.
And one of these this standard conclusion that was in this literature was that people tend to come up with a more restrictive kind of rules, while he was thinking of the more easy one or the more general one. So in what you described here, if I understood correctly, there was only one correct kind of categorization. And I was thinking, what would happen if you had different levels of categorization in terms of complexity? Would humans go for the more complex one while the path would go for the easiest one, or vice versa, or something like this?
Yeah, that's a cool question. So like the way that the Watson selection task is sometimes framed is it's for active testing. So it'd be like, so like in the Vanguard problems, we give people the scenes themselves rather than like a person proposing a scene and then getting feedback on what it is. And we don't have that mode within paths. We don't have this mode where it's going to say, oh, I think I know what the concept is, and this is the scene that I would draw in order to get information on it. And that would be really cool to have that version of it, the active learning version of it. So there's a sense in which what you're asking is just beyond paths. Now we can do the version where you say where there's two different rules, an easy and a hard one. I mean, it actually came up a little bit in the 1 versus 2 problem that I showed you, because it was also true that the objects on the right were a little darker than the ones on the left, and nobody mentioned that because it didn't seem adequately interesting, I guess. So I think that there's a good reason for us to have the problems that have only one solution, because otherwise, it would be too, I guess, too easy probably for the system to come up with something, and it requires quite a bit of I don't know, challenge or taste in coming up with the Vanguard problem, so that you look at it and you can't come up with another interpretation. So oftentimes when people come up with Vanguard problems, it's iterative. So you come up with the Vanguard problem and people come up with a solution that you didn't intend, and you look at it and you say, oh yeah, that actually is a valid solution. Like Steve saying they're all letters on the left. Now, right, and so there we can quibble about whether that was a good solution or not. But you definitely want a Vanguard problem that doesn't have that. But so it's absolutely true for paths. If you gave it a problem that had an easy and a hard solution, it would be totally happy with just spitting out the easy solution. So, and I believe, roughly speaking, that would be true of humans too.
Thank you.
You go, Jay.
No, so I think I remember hearing about this, that like GPT-4 is pretty good at Vanguard problems. I mean, didn't Keith Holyoke and people have some study where Melanie Mitchell was doing somebody?
Melanie Mitchell was arguing against this Webb and Holyoke. Yeah, so and they did like the copycat problems too, and it's not clear how many of them were in this training set. I mean, the big problem with ChatGPT is we don't know what its training set is, and for the copycat and analogy problems that it was trained on, there's reason to think that they would have been in the training set. They had enough uptake in the community so that they could have been there. When Melanie then came up with brand new copycat problems, it was not very good at it. So there is work on, can you guys, I think the Zoom people are no longer seeing. Oh, no, I guess you are. So there are other systems to solve bond graph problems besides ours. And maybe the state of art systems are the two bottom ones that use a CNN and classifier systems, and they do awful on ours. So they are not, so I would maintain that current deep learning systems do not do our problems at all very well, which is part of the reason why this is an interesting challenge, you know, in the sense of we're trying to justify humans existing. You know, so this is a hard problem to do, and largely for deep learning systems because you're able to come up with a solution with only 8 objects per side. And of course, they're pre-trained on millions and millions of objects. But the Ewan system does, you know,
Even if you could get GPT-4 to do it, I bet it wouldn't. I mean, your model has the intuitive sense of testing hypotheses, and you know, whereas if you just kind of like feed forward, spit out an answer immediately, then it's not like a human.
Well, but okay, I think that's true, but I'm sure it's a mug's game to be betting against the next iteration of the deep learning models. But I would be surprised if you're talking about open-ended generalization, if a system that didn't have a virtual physics engine, for example, would be able to solve these, just because it's hard to figure out the answers to these. And I don't know, I feel like it's sort of like a generative adversarial network. So I feel like there's going to be like a next generation of people creating new problems, so that, if there was this sort of artifact or a confound that you could take advantage of with the previous convolutional neural networks, then you'll be able to create a problem that would test that. And so that's the enterprise that I think we could be engaged in. And where it seems to me the logical development here is that these deep learning systems will be forced to either create a virtual physics system, or they will have a virtual physics system emerge within them. And that latter solution, I think, is going to require a different algorithm. I just don't see it.
Yeah, if we want to go on another couple of minutes.
Yeah.
Okay, yeah, I got, I guess, 2 questions or observations. The first question is, have you compared the internal descriptions that the machine produces to what people do? Because all I've seen, I think, was performance data.
Yeah.
You plotted performance, human against machine.
Right.
But have you actually looked at, since the emphasis of this is on dynamic descriptions, have you looked at how people describe this?
So we've looked, so at the end of paths, it gives you in green what it thinks its description is. So we compare those to the human descriptions, and
So your humans tell you what they think is going on.
Yeah, they can. So we have 2 ways of measuring human performance. One is they actually use the type out what they think is the rule, and the other is we give them new examples of the problems and they have to categorize them.
Right.
And that'd be more like the deep learning kind of approach.
Okay.
So yeah, in the results I was talking about is basically the first. It's quite good. You know, just ask people, and it's quite effective way of getting what they think the right answer is.
And they say the same thing as what Path is picking up.
Roughly speaking, they don't use the same words, but you can code for the gist. And the gist is the same, except for on problems where we misdesigned them and there was multiple solutions, say. Yeah. Okay. And we try to get rid of those on the second iterations. Yeah, so I think but the other version of your question is that you saw this list of hypotheses that Paths was considering on the way to building up, and I don't know how to get at those for humans.
Yeah, right.
So that would be interesting. That would, I guess if I'm taking this as a strong cognitive model, then there should be similarity of those too.
But how would you get that?
Yeah, and it feels, I mean, they feel kind of weird, so some of the.
Talk about protocols, could you?
Yeah, right, yeah. These things are so fast though for humans, I mean, and it's hard for people to put into words, yeah, that's interesting. But that, so yeah, I would be interested in seeing how you would get at that. If I look at the hypotheses, some that passive screening seem pretty convoluted and weird and unlikely to be true, so I think there could be some refinement for those. So it feels like the final products are actually better than the intermediary products for at least fitting my intuition. Yeah.
And the final question I had was, when you sort of talk about this, I always get the impression that you have this interaction between perception, categorization, and description is kind of changing what people see in the object.
Yeah.
Right, that's sort of the intuitive description.
Yeah.
So the question then is, whatever it is that people are ultimately perceiving, does that have some sort of lasting consequence? So in other words, half an hour later or whatever, 10 seconds later, if I show you this object, do I still think it's a cat or an elephant or whatever? You know, the example you mentioned over lunch of Jeff did.
Right.
So in other words, is there a trace of this on people's perception outside the context of the problem sort of downstream?
Yeah, so I would say that yes, probably, there's certainly a trace of the description that was built up and is critical to pass for other things that you're noticing in other scenes.
Oh, so a sequence.
So we can do it in sequence. We do some of these in sequence.
And do people show the same sequence?
So like once you've detected that this scene has a support relation in it, you're far more likely to see support relations in downstream scenes. That's not exactly your question.
Well, it is actually that.
And the other thing that we haven't systematically looked at, because PATH doesn't do it, is priming for other problems. So if you gave people a problem that was support-based, they're going to be much better at solving other support-based problems, right? And so that is not, again, it's not how you're interpreting that one scene, but it's really how you're generalizing the notion of support. And so PATHs, I would say, I don't know what learning is, but I would say PATHs does within Vanguard problem learning, because it applies what it's noticed in one scene to other scenes, but it doesn't currently have cross Vanguard problem learning of that kind that I was just mentioning. There's definitely things in the architecture that would make it super easy to put that in, because you can have, most obviously, you can clamp how important certain features are. And if something is important for the previous problem, you would, it's reasonable to think that you would clamp that on. Yeah.
Well, if there are any further questions, I think we can stop here. So thank you very much.
All right, thank you.
Thank you to the people online still attending. And thank you to people here. I'll see you next week, I guess.
Sounds like a plan.
Bye-bye.
Bye.
Bye, thanks.
Thanks, Ron. So